This is EE542 Lab 6 Internet Router Experience. Here we will gain some experience setting up static routing on the small network. As per the diagram, we have 4 hosts and 3 routers. We'll set up the router so 4 hosts can exchange packets as per the topology. We already made account on AWS Educate. Here we have permission to use 5 elastic IP addresses. Here we will create a VPC with 10.0.0.0/16 and then we'll attach it with internet gateway and we'll add 0.0.0.0/0 to point to internet gateway in its routing table. So we'll go to AWS Educate account and create a VPC. Here we already created a VPC. Now we will create subnets as per topology. We choose an availability zone as US East 1A. This will be one subnet which will be from between router 1 and router 3. We can see here one subnet is created. We can create other subnet similarly. We can see here there are total 5 subnets. We have created 5 subnets for the topology. Now we need to create network interfaces for routers and hosts. Here there are 3 routers. 2 routers have three interfaces and one router has two interfaces, and each host has one interface which will connect to router. We already have internet gateway attached to our VPC. That we have added this route to our routing table to reach internet gateway. Now we'll go to EC2 instance tab, and we'll create network interfaces. Let's create router 1 to 3 as per topology. This will be the interface. The subnet name will be router 1, 3. We need to assign custom IP address, which is this 10.0.10.20. I've already made a security group which consists of inbound and outbound traffic of TCP, UDP, SSH, and ICMP. The inbound outbound traffic is for all, and inbound traffic is for this all four protocols. We'll create for others. Router 3 to 1 interface. So this way we'll create more static interfaces, network interfaces. We still need 4 more interfaces for hosts. Now we have total 12 interfaces, network interfaces for topology. You can see here. Now we will launch instances, which will be VM for router and nodes. In EC2, we'll launch instance. So we'll select 64-bit ARM architecture of Ubuntu Server 16.04 LTS. We'll take E1.large, which has 2 CPUs and 10 GPS speed of the links. Okay, so subnet is router 23. To disable auto-assign public IP. We'll use a subnet of nodes for router 1, so we can set our primary interface should be the one which is connected to router or connected to node. Second interface will be connected to router 123.0.60. Use the security group. This is a private key. I have already downloaded the key. Okay, so my instance is created. Let's view the instances. So this is instance for router 1. Let's write router 1. Now I'll create it more instances, total 7 instances. So here we can see we have made total 7 instances, 3 for routers and 4 for nodes. We also attach network interfaces to each instances according to our topology. Now we have to log in into these instances from our command window from host PC. Here we can see that we have attached elastic IP to our instances. Since in AWS Educate account we can only use 5 elastic IP addresses, I have attached node 1 and node 3 instances with elastic IP addresses. Later we'll see how we can manage with 5 elastic IP addresses in 7 instances. Now we will SSH to our instances. I have already SSH to node 1. Let's SSH to node 3 instance. Now we will SSH to other nodes and routers. As now we have SSH to all 5 instances, 2 nodes, node number 1, node number 3, and all of the 3 routers. So when I write ifconfig -a, we can see all the interfaces. Now we will edit the interfaces file to have IP assigned from AWS DHCP server by writing this. Here interface for router 1 and 3 will be EN6 ENS7, and for router 2 it will be ENS6, and we'll save the file and reboot. We need to add DHCP for its ENS6 interface. Okay. We'll do it for other two routers also. We'll do this one NS6 and 7 both for router 1 and 3. Do it for the third one also.
Hi, I'm Aditya, and I'll be covering the rest of the demonstration for the lab 6 of the course EE542. So, I'll be starting from the section where I'll be covering the building and the installation of the Quagga router on our network topology. So, as you can see, I'm at the stage where I have already changed the QDIS configurations for routers. So, this is my router 1, this is my router 2, and this is my router 3. And this is my node 1 and this is my node 3. So AWS has a limitation that we can only use 5 elastic IP addresses. So I'll be accessing my node 2 and node 4 via node 1 and node 3 through the SSH protocol using the private IP addresses. So as you can see, the first question that I was posed in the problem statement is that can node 1 ping node 3 or can node 1 ping router 1. So this is my node 1, this is my node 3. So let's try that. So if I try to ping my node 3 which has the IP address this, you can see that I'm not able to ping my node 3, right? Because as you can see, I don't have any details about the 10.0.2.0 in my routing table. So, but if I try to ping my router 1 interface, network interface, 1.20 is the router interface, you can see that I am able to ping router 1. So the thing is, the default router points towards the address which is assigned by AWS. So as you can see, it's 52.1 and 50.1. We want the default IP address to be pointed towards the routers in our own topology. So for node 1 and 2, it should by default point towards router 1, and for node 3 and 4, it should by default point towards router 3, right? So for that, we use a command called IP route change. So let me show that. But yeah, before we do that, before we change our default, we have to go through certain steps so that we don't basically don't break our SSH access link. So if we change our default route, we might not be able to access our nodes. So for that, the steps that was given to us is to basically add a route using a global IP via the AWS assigned router gateway. So let's see that. So for me, it's 138.88.156. So I'll just copy this command just for the ease of it and paste it. And I'll make the changes based on what I have. So here, instead of 30, I'll have 50, and instead of these values, my global IP address is 88.156.0. That's already there. So in this way, our SSH won't break down because we added our global IP address of my own PC. So whenever I'm getting this, it'll be via through the AWS router. Right? We do the same there as well. With a minor change that we change this to 52.1 because that's the default AWS router, and my global IP is going to be the same. So we do that, and the next thing we do is change the default router. So we do that via sudo IP route change default via. So for node 3, so then this is my node 3 and this is my node 1, right? So for node 3, the default should be pointing towards router 3, which is 10.0.2.20. That's going to be a default because our topology says that this is the interface which is connected to the host. So the node should be pointing towards this particular IP address. So we do that, and thankfully you can see that my search is still running, and let's see if we can. Let's make it this way. So yeah, now you can see the default is pointing towards 10.0.2.20, and I'm still able to access my SSH because of the global IP route that we have added. So we do the same here as well. So what we do here is sudo IP route change default via 10.0.1.20 for node 1. So our SSH is still running. That's a good sign. And as you can see, now this is a new IP route. So by default, node 1 will point towards router 1 and node 3 will point towards router 3. Now we do the same thing for our nodes which are not which don't have an elastic IP address. So we access them by our private IP address. 1.11 is the IP address for my node 2. So we do that and say yes. As you can see, I'm now logged into my node 2. I'm in my node 2 right now. So IP route here, we have the same problem here, right? So first I'll just copy whatever we did. So I think it's already copied. So yeah, it's already copied. So instead of 50.1, we make it 51.1. We add that and then sudo IP route change default via 10.0.1.20. SSH is still running. IP route all done for node 2. So by node 2 is also pointing towards router 2 now. We do the same thing here as well. We do SSH -i keeper 10.0.2.11. That's my node 4. Log into my node 4, IP route, same issues, so we do the same thing. Instead of 50.1, we change it to 53.1 because that's the default AWS router given to this particular node. And pause it. And then we do the same thing, sudo IP route change default via 10.0.2.20 IP route. Yeah, so that's how we are able to make our nodes point towards the router by default, the routers that are in our topology. So now we basically clone the Quagga Git repository. So we were told to make our own directory, and I'm going to clone it here, so on the routers, and all that's done. So the next step that was given to us was to run this command after we check out the files, right? So I might have to go into my Quagga repository and then I'll do like this. So I'm guessing this might take a bit of time, and I'm going to pause the recording here and I'll play once that's done. So the script just ended. Now I'm gonna run this command on all the 3 routers, and same as before, I'll pause the recording and I'll play once it's done. So now I'll run make and I'll continue the recording once this is done. So now the make is done. So now we have to create a configuration file on all the 3 routers, and we might have to name it zebra.conf. Yeah. So zebra.conf, and I already copied it on my this thing. So this one is our router 3, so I might have to make some changes. This will be 2.20, this will be 10.21, and this will be 20.20, and that's it. So just to confirm, I'll quickly run an if config. Yeah, 2.20, 10.21, and then 20.20, and the loop back. So that's what we have in our 2.20, 10.21, 20.20, and oh, I just realized this should be on the next line. I think, yeah, it should be on the next line. So this is done, and this. We do the same thing here. Zebra.conf, paste it here, quickly make this change before I forget, and this is same as my router 1, so it'll have 1.20, 10.20, and then 30.20. Right, so this is the host name ZebraD, and this is the password for our Zebra daemon. Let's double check into if config. Loopback is the last one. 1.20, 10.20, and then 30.20, and then the loopback. So that's the original order that we had. If you can see that, 1.20, 10.20, and 30.20. Yep. choose the name here, zebra.conf, paste it here. So router 2 has only 2 interface, so we have to delete this particular line. We don't need this, and the above line, and our interface 5 is 20.21 and our interface 6 is 30.21, and then the loop back. Let's confirm that. 20.21, 30.21, and the loop back. So that's what we have, right? So the next steps would be to basically delete the existing default routes, and we follow the same procedure. So if I do IP route, you can see that the default route is pointing towards the AWS router. Since the 3 instances that we are running in the middle are routers in itself, we don't need a default gateway for those routers, because we are making these act like a router. So we have to delete that, and before we delete that, we have to basically make sure that the SSH isn't broken. So we do the same step that we did for our nodes. So let's quickly see what we did. Yeah, so we did this, right? So sudo IP route add. I'll copy this from here. Oops, yeah. Let me clear the screen because the window is small. IP route add. Yeah, so instead of 50, I would have 2.1, right? Yeah, 2.1. So this will be 2.1. I'll do that here. Copy. This will be 1.1 for me. I'll do it here. This will be 20.1. Right, because the default is 20.1 for our AWS router. 1.1. That's why. So now if we add IP route, you can see that the global IP route is added to the routing table, and now we can go ahead and delete our default. Sudo IP route delete default, and we can see that our SSH is still running, so that's a good sign. Default sudo IP route delete default, and we run the IP route again to confirm that we don't have a default route. Oops. Yeah, so as you can see, our default route is out. It's not on the routing table, so these will act like a routers now. So the next thing that we're supposed to do is to basically start the Zebra on our routers. So I'll just copy this here. I might have to go inside the Zebra folder. It's there. Yep, it is there. So cd Zebra, cd Zebra, cd Zebra. Right. I'll just paste it. Yeah. So how will we know that it's running? We'll execute this command basically. What's our password? If you remember, it's Zebra, and we are in the Zebra daemon. Zebra. Paste it here, and then Zebra. Yep, we are in the Zebra daemon. So the next thing that we have to do is that we have to let router 1 know that there's a network 10.0.2.0 which the router 1 is not aware of. So you have to statically add routes for on router 1 and router 3. So that's our first step. So we'll do enable configure terminal, and we'll add IP route 10.0.2.0 2.0/24, 10.0.10.21. This is our gateway. So 10.21 is our router 3 interface. So whenever router 1 gets a message that is supposed to be in this network, it will pass it on to 10.21 router gateway. So we do that. I'll exit and if I run show IP route, it will show me that the static is added. So by default it's pointing towards ENS6 because the 10.0.10 is on my ENS6 interface. So I'll do the same thing here. Enable, configure terminal, and then IP route 1.0. Why? Because the router 3 is not aware of this particular network, and the gateway will be the router 1 gateway. Right, exit and show IP route. You can see the static command has been added. So let's just try pinging. So I'll ping 10.0.2.10. I'm pinging my node 3, and as you can see I'm able to ping my node 3. We do the same. We try to ping node 1 from node 3, 10.0.1.10, and as you can see we are able to send packets, ICMP packets. So let's try for the node that is not here right now. So node 1 is here, so I'll try to ping node 2, 10.0.1.11. we are able to ping. Now I'll do the same here as well, and 1.11, sorry 2.11, and I'm able to ping packets. So as I showed before, that I'm able to ping my node 3 from node 1. So as you can see, I'm getting an RTT of around 5.6 milliseconds. The reason is that because we had given a delay of 2.5 millisecond on this particular link. So the interface on the ENS6. So ENS6 is basically the link between my the interface is just connected towards the router 3, and let's show. So an ENS6 again is 2.5 milliseconds, and that's the interface that's connected to the router 1. So 2.5 from here, and then 2.5 from here, so it's around 5 milliseconds in this link in itself. So that's why we are getting some 5 point something milliseconds as our RTT. So the next steps that the problem statement tells us to do is to configure our router 2. So right now we are able to ping because of the link router 1 and router 3. So we didn't do any change on our router 2, right? So for that, I'll run the telnet again, zebra, and I'm in the zebra daemon, configure terminal, right? So router 2 doesn't know about both the 0.1 address or also the 0.2 address, so we add both of those. IP route 10.0.1, so let's start with 1, let's have 2, okay, 0/24. So if it's getting the packet 2.0, we need it to go via router 3, right? So 0.20.20, and for addresses in 0.1, 10.0.1.0, we needed to go via router 1, so that will be 30.20. right, exit and show IP route. As you can see, the 2 static addresses have been added, right? So let's do a trace route. Trace route 10.0.2.10, and same thing on trace route 10.0.1.10. So trace route will give us a how many hops away is our destination, along with the ping, along with the RTT basically. So as you can see, first we'll go towards the route interface, and then this is router 3, and then the destination. So traceroute is showing us this path, and it's not going via the router 2. Why is that? Because in Zebra, it's like a first come first serve sort of ideology. So whatever command, whatever routing table has been added, it'll prioritize that. Oops. So I do telnet Zebra show IP route. So yeah, you can see that we have given this as our path for us. We haven't added the secondary path on our router 1, and we haven't added a secondary path on our router 3, right? So let's try. So the question that's posed to us is that can router 2 ping any of the nodes in the LANs, right? So let's try pinging that. Let's exit from here. Let's try pinging 10.0.1.10. We are able to ping because now we have added the route, right? So we are still getting 5 milliseconds as our RTT because we have added delay on our router 2 as well, right? So this show, as you can see, we have added delay on both of our interfaces. So one interface is connected to router 3 and one interface is connected to router 1, right? So we are able to ping our nodes that are on this 10.0.1 network. Now we'll ping 2.11, and as you can see, I'm able to ping now. So the question was asked, why not? Because we didn't make any changes. So now, since we have added the change, added the 2 routes, we are now able to ping different LANs. So now this next step is to add a secondary route through router 2 on router 1 and router 3. And yeah, so let's try that. Let's do a basically telnet Zebra. Oops. Yeah. Enable configure terminal. Right. So now we add IP route 10.0.1.0. Sorry, 2.0. 24. It should go via 10.0.30.21. So that's the gateway that is connected to router 1 on the router 3 interface. Oh, sorry, router 2. Do that, and we do the same thing here. Configure terminal IP route 10.0.1.0 / 24 10.0.20.21. That's what we are supposed to do, right? We exit. Let's exit. Show IP route. So as you can see that we have 2 ways now. So either directly going to router 3 or taking an extra step going to router 2 and then router 3 and then the destination. Same way for this thing. So let's try pinging on both of our nodes. We are able to ping, but let's run trace route. Let's see what that gives us. So as you can see, we are able to ping, which is expected. But let's run trace route. Yeah, so the first hop is the from node 1 to router. That's the first hop. And the second hop, it's telling us that it took router 3. So it'll jump to router 3, right? And the last hop is the destination. So it's just showing us 3 hops. It's not going via the fourth one. The reason is that because it will first prioritize the one that's above the preceding one. So first, if it's going towards 10.0.24, it'll first try the router 1 interface. It'll go in an order basically. So that's why we are having only 3 hops. So 1, 2, and then 3. Same way from the other side. So now what I've done is I've added extra distance between the router 1 and router 3 link. So as I said that the trace route is going via this route, right? So it's not even considering this route, and even the ping is going via this route. So what I am doing is right now is that I'm increasing the distance for the router 1 router 3 link. So this has 5 and this distance metric has 1. So it'll prioritize the one that has the shortest distance. So that's why, as you can see, I have an asterisk here. That means it prioritized this for this particular address. Right, so I do the same here. Enable configure terminal, and then IP route 10.0.1.0 is the address the router 3 knows. So I'm increasing the distance for this particular link. So this is 10.20 space 5. Exit, show IP route. So as you can see, the asterisk is on the 20.21 address. So let's run trace route again just to see if the number of hops change and even the RTT changes. So as you can see, in the previous case, when we went from 2.10 to 2.20, we had a delay of 0.117 because the delay is not added there. Then we had a 5 milliseconds delay to reach here because it's 2.5 milliseconds on this router and then 2.5 milliseconds on this router. And then we have 5 milliseconds here again to come to 1.20, right? So as you can see that tracer is giving me an error here, but the number of hops is still more. So first it goes to 1.20, so instead of going to 10.21, it's going to 30.21. But we can see that the third hop is giving us an error, and I'll address that in the later stage. So let's try pinging. Let's see if we have any change on the RTT. So as you can see, the time is now 10 milliseconds as compared to what we had 5 milliseconds there, because the 2.5 milliseconds delay is added here as well, so in this link as well and in this link as well. So that's why we have like 2.5 plus 2.5 plus 2.5 and then plus 2.5. So that's why we have around 10 milliseconds as our delay. We'll do the same here, 1.10. We still have the 10 milliseconds delay overall, right? So now what we have to do is we have to drop the packets 100% between the link, between the router 1 and router 3 link. So let me just do that. Oops. Exit. As you can see that my link has 2.5 milliseconds on both of the interfaces, right? So I'll change that to basically to a higher amount. So sudo tcqdisk change, I might have to refer this thing, yeah, change dev. So the interface that is connected to my router 3 is ENS6. So I mean just to be on the safer side, I'll just do an if config, because if I do it on a wrong interface, I might break down my SSH. Yeah, so 10.20 is the one that's connected to this thing. I'll do this the same here. Yeah, 10.21, right? So tcq disk change dev DNS6 parent 1:1 and 10 rm delay is 2.5 milliseconds. I'm guessing, yeah, 2.5 milliseconds, and drop 100% of the packets. So RSS is still running, so that means we have applied to the correct interface. And since it's the same ENS6 for router 3 as well, we'll just copy and paste it and then hit enter. Right, so if I tcq disk show, yeah, so technically the route between router 1 and router 3, the link between router 1 and router 3 it's very bad. So, and because we have added a metric to it, we have added the distance 5 between the router 1 and router 3 link, it'll always prioritize this path. So it'll go via router 2 always. So if our ping is working, then we are good to go. And you can see that our ping is working even if we have a 100% packet drop on this particular link. We'll do the same thing here. 1.10. As you can see, I'm able to ping node 1. Yeah. So as you can see, the IP route is the routing table on that is loaded on my kernel. So as you can see, the address for 10.0.1 it's going via router 2 because the metric is smaller in this case, and you can see that is set by Zebra. It's not a direct connection, it is set by Zebra, right? So it's the same for here also, Zebra, and it's prioritizing the path via router 2. Why? Because you have decreased the metric so that it doesn't go via the path where the packet is dropping 100%, right? Oops. So this link, router 1, router 3 link, has a 100% packet drop. So that's why we increase the metric in this link so that this is prioritized. The router 2 is prioritized. So let me just run a trace route. Right, so this is my node 1 and this is my node 3. So I just want to answer a couple of questions that were asked to us. So as I showed that I can ping from different LANs, and the delay is more because there's an extra hop. We are going via router 2, and so basically when I do a trace route, I can see that the third hop is giving me an asterisk, right? So that the question is that why we get this. So the reason is that because for node 1 and 2, the default router is router 1, but router 1 doesn't have any information regarding the network that is between router 2 and router 3, right? And this address is 10.0.20.024. So as you can see in my routing table, the router 1 has no clue about it. That's why it's not there on my trace route. And this is the same reason for the 3 asterisk error on node 3 as well. So router 3, which is the default router for the nodes 3 and 4, doesn't have a clue about the network link between router 2 and router 1. I think the address space is 10.0.30.0. So as you can see, this is not there on the routing table for router 3. So this is the reason why the third hop is always the 3 asterisk, because the third hop, so this is the first hop, second hop, which is known to router 1. The third hop is this hop, which is not known to router 1, right? And the fourth hop is the destination. So that's why we are getting the destination. So it's the same way. the other way around, right? So changing the metric, it did fix the network. We are not facing any more packet drop because it's not going via this link. And the next question poses, how long do you think it will take you to change or update the routes manually if you worked at ISP? So yeah, if looking at the level of ISP, it will obviously take a lot of time. It's not scalable, because as you say, I have to manually edit the IP route table if I'm using static routes. And if I have like 4, 5, 10 routers, I mean, the links, the networks will always be more. And this would basically be a really cumbersome process. Do it manually, and it's not feasible. Basically, it's not feasible to, manually go to 5, manually fill the routing table, and it's a really cumbersome process. So it does not scale well with the increasing number of network. Now protocols like OSPF will be able to solve the problem, and so you can break down the OSPF protocol in basically 6 major processes. So first step is the initialization step. So it's in the initialization step, routers basically form relationships. So they get to know who the neighbors are for that particular router, and then once the information has been exchanged, they go into a two-way state. So after the two-way state, once the designated router or the backup designated router has been elected based on the router IDs, they go to an Xstart state. So Xstart step is where they sort of act like a master slave uh, ideology, and once that has been established, they go into an exchange state, right? So when they're in exchange state, they basically do an link state advertisement of their DBDs, descriptions, basically what all routing table that they have. So the routers will then communicate with each other regarding the route which is not in their routing table, right? So in this way, all the routing tables, all the routers have all the details about all the networks in the neighborhood, right? So in our case, we don't have no clue about the network that is between router 2 and router 3. But in OSPF, all the routers know about all the networks in the neighboring topology. So once that is done, the cost calculation is the last step during the loading, during the full state. So the cost calculation is done based on the link bandwidth. So higher the link bandwidth, the lesser the cost is, and the more the probability that the packets will be routed via the path which has the lowest cost, right? So if the link between router 1 and router 3 is bad, which is in our case it is because we have a 100% drop, right? So in this case, this link will have almost a very small bandwidth. So the smaller the bandwidth, the higher the cost. So that's why open shortest path first, that's the full form for OSPF, won't prioritize going via this route. So it'll prioritize going via router 2, even though it's an extra hop, but we don't face the case where we have to drop the packets, right? So that's how OSPF can solve the problem, and we don't need to manually change the routing table because that process is taken care of by the DRs and BDRs methodology in the two-way state. And yeah, so that concludes the demonstration of my lab 6, and thank you.